Hello guys, how are you? Last class, I think we are discussed the nomenclature of cation. Nomenclature of cation based on oxidation state, right? Yeah, ferrous, ferric, cuprous, cupric, mercurous, mercuric, stannous, stannic, which means if a cation or if a metal can exist in two different oxidation state or two common oxidation state, ready? Then the lower among that common oxidation state, which is end with a suffix of "s" and higher ends with a suffix of "ik," right? Now we can discuss, or now we can extend the same concept into oxo acids. Oxo acids. Oxo acids. What do you mean by oxo acids? Acid having a double bond O group to the central atom, right? Double bond O group to the central atom. Oxo acids of phosphorus may have a P double bond O. Okay, so acid with the oxo group. Oxo group is double bond oxygen, ready, which is directly attached to the central atom. Such kind of acids are said to be oxo acids, ready? And oxo acids of so the concept of nomenclature based on oxidation state in your oxo acid. That means lower OS, oxo acid with the lower oxidation state end with the S acid, whereas oxo acid with the higher oxidation state may end with the ic acid. Ready? I'll give you example. Listen, the most familiar examples: H2SO3, H2SO4. Ready? What about the oxidation state of H2SO3? And now you're able to calculate the oxidation state. You know the whole rules. Okay, there is no exception. It's a common one. So H2SO3, sulfurous acid. H2SO3, the oxidation state of sulfur is +4, whereas in H2SO4, the oxidation state is +6. And H2SO3, which is said to be sulfurous acid. Sulfurous acid, because it is a lower oxidation state. And H2SO4, which is said to be sulfuric acid. You know that it is a well familiar name, right? Sulfuric acid. Everybody know. Each and everybody know that sulfuric acid. And listen, and with the higher oxidation state of sulfur, which is in +6, that's why the name is sulfuric acid. Okay. So here, sulfurous acid, and here sulfuric acid. See the difference. Okay, I'll give you one more pair. Have HNO2, moreover HNO3, two different oxo acids of nitrogen. Fine. And here the nitrogen is in +3 and here the nitrogen +5. Listen. And you know this is said to be nitrous acid. S acid, because it is in the lower +3 oxidation state. And this is said to be nitric acid, because it is in the higher oxidation state. So the concept of S for lower and ic for higher, which is also applicable in your oxo acid. And what about the case in oxo anion? Oxo anions. Let us discuss the case in oxo anion. Oxo anion means hydrogen is removed from corresponding oxo acid. I have an oxo acid. Let it be H2SO4, oxo acid of sulfur. There are two hydrogens, right? And two hydrogens is removed. Then it will be SO4 2-. And that is the oxo anion. Oxo anion, like that. So what is the change in a suffix of oxo anion based on oxidation state? In the case of lower oxo anion, the lower OS may have a suffix of ITE, and the higher OS, higher oxidation state, may have a suffix of ATE, Lower OS with the ITE and higher OS with the ATE. Ready? Fine. Listen. Let me have some example. SO3 2-, and you know from where the oxo anion is formed, from your H2SO4, H2SO3. and the companion of that one is SO4 minus. And you know that the oxidation state is still same. Here also plus 4, here also plus 4. Okay. If hydrogen is removed, then there is no change in your oxidation state. It will be remains the same like that. Okay. But the name have some kind of change. This is ends with the S acid, but now it is in a lower oils of anion. So this one will be sulfite ion. Sulfite ion, you know the common term. And this may be sulfate ion. Sulfate ion. Sulfite ion and sulfate ion. Okay. What about NO2 minus and NO3 minus? NO2 minus and NO3 minus. For NO2 minus, the oxidation state of nitrogen plus 3, and here we have plus 5. Plus 5. And this is a lower one and this is a higher one. Ready? Fine. Listen. What about NO2 minus? Nitrite ion. Nitrite ion. And NO3 minus? Nitrate ion. Because this is a lower one and this is a higher one. So nitrite, nitrate, like that. And you can check it in your halogen acids. Listen. Oxo acid of halogen. Oxo acid of halogen. Halogen having 4 different kind of oxo acid. HXO, or it is otherwise said to be HOX. That's the first category. The next is HXO2. The next is HXO3. The next is HXO4. What is the difference? The oxidation state of halogen is plus 1, plus 3, plus 5, plus 7. Okay? Ready? So listen. What about the names? Listen, listen, listen. Listen carefully. This is a lower oxidation state. So plus 3 is the lower oxidation state. Then what about plus 1? It is a lower oxidation state. Something which is less than lower oxidation state. So plus 1 is a very much lower oxidation state or lowest lower oxidation state, and plus 3 is the lowest oxidation state. And plus 5, let plus 5 be the highest oxidation state. And what about the plus 7? That is a maximum case, most highest oxidation state. Okay, so the lowest oxidation state, that is plus 3. So this is the oxo acid of halogen. So that is said to be Halous acid. Halous acid. Why it is Halous? As that is for lower oxidation state of oxo acid. So now simply you consider plus 3 as the lowest and plus 1 as the most lowest and plus 5 as the highest and plus 7 as the most highest, like that. Okay. So since plus 3 is the lowest one, simply it is Halous acid, and plus 5 is the highest one, it is halic acid. Halic acid, because that is the highest one. Then what about the most lowest one plus 1? Most lowest one plus 1, it is hypo. They're having a some term also, some more term also, that is hypo. It is not simply Halous acid. It will be Halous because that is the lowest one, but it is not only Halous. They have an additional term hypo. Hypohalous acid. So the most lowest one, that is in plus 1 oxidation state of halogen. Oxo acid with the plus 1 oxidation state, that having hypohalous acid, having a name of hypohalous acid. And what about the most extreme, most highest one? That having, it's not hyper, it is simply per. per Alice acid. You know, hypo means lowest. Hypo, hyper, like that. And there is no hyper, it is simply per Alice acid. Ready? Then what about its corresponding oxanion? XO minus, XO2 minus, XO3 minus, XO4 minus. What about the names? You know, in XO minus that is +1 and here +3 and here +5 and here +7. Okay. So lowest will be IT, highest will be AT. So this is the most lowest one. So this is hypohalite. Hypohalite. And this is a simple lowest one. So this is simply halite ion. This is the highest one. So this is halate ion. This is a most highest one. This one will be perhalate ion. Perhalate ion. So these all are the ideas. These all are the ideas which is in consideration based on oxidation state of different nomenclature based on oxidation state for your cations, anions, oxides, etc. Ready? Now, let's check some examples. Okay, let's have some more examples. That is, I'll give you some salts and let's check how we can name it. Okay, we have FeCl2. FeCl2. So Fe, it is not pronounced as iron, and you simply check the oxidation state of Fe here, and you know how to check it. Okay, so since there is 2 chlorine which offers -2, the ion will be +2. So oxidation state of iron is +2. So this is lowest oxidation. Iron with the +2 which is said to be ferrous. So this is known as ferrous chloride. Ferrous chloride. Listen. And let's have Fe2O3. Fe2O3. Okay. You simply find the oxidation state of iron and you obtain it as +3. And you know how to find it. So this one will be ferric oxide. It is not ferrous. The iron is now, it is in ferric because it is in +3. So it is ferric oxide. Okay. CuSO4. CuSO4. Ready? CuSO4. And now you know the copper is +2 oxidation state, right? So it is cupric and SO4. Cupric SO4. So it is cupric sulfate. Cupric sulfate. And there is no cuprous sulfate, right? Cuprous sulfate having a formula like this. And cuprous sulfate is not existing in nature. Okay. So that's why it is otherwise said to be copper sulfate. So no need of mentioning it as cupric. Copper is enough. Okay. But in the case CuO, Cu2O, what is the difference? Here the copper is +2. So this is copper oxide. This is copper oxide. It is not termed like that. Okay. Or it is not said like that. Because there is a contradiction. If you simply say that copper oxide, then there is a chance whether it is CuO or whether it is Cu2O. So you have to mention that, okay? So this is in a +2 oxidation state. So this is said to be cupric oxide. Here where the copper is in a +1 oxidation state. So this will be cuprous oxide. See the difference. Ready? Okay. And let I have KNO3. KNO3. So K potassium and NO3, nitrogen is in the most one, +5 oxidation state. So nitrate. So this is said to be potassium nitrate and NaNO3. NaNO3. Where nitrogen is in the NaNO3, no need of NaNO3, let it be NaNO2. Nitrogen is in the lowest oxidation state. So this is sodium nitrite. Ready? Is it okay? Fine. Listen. Let I have KiO4. And this is an oxoacid salt, right? Oxoanion, where the iodine is in the +5. Something like XO4 minus. Perhalate ion. So here the halogen is iodine. So it will be periodate ion. So this is said to be potassium periodate. The next, let it be in the next NaClO2. What about the oxidation state of your halogen? Halogen is in the +3. +3 is not most lowest. It is simply lowest. Simply lowest ion having a name of halide. Since it is chlorine, it will be chloride. So with sodium, it will be sodium chloride. Sodium chloride. Ready? Okay. Okay. The next is NaOCl. What about the oxidation state of chlorine? That is +1. Then it will be sodium OX minus. Where the halogen is in +1. Hypohalide. So sodium hypochlorite. Sodium hypochlorite. Ready? HgCl2. Where the mercury is in +2. And there is HgCl also. Or Hg2Cl2. Dimer form. Where the mercury is in +1. So we can't say that it is mercurous chloride. Mercury chloride. You have to mention whether it is mercurous or mercuric. So here +2. So this is mercuric. So mercuric chloride. And here we have, tell me, here we have +1. So it is mercurous chloride. Mercurous chloride. Ready? Let I have KBrO3. So bromine is in +5. So this is the highest case. It's not most highest. So highest having a name of halate ion. Since it is bromine bromate ion. Along with the potassium, it will be potassium bromate. Okay, so this is how the salts are named on the basis of oxidation state. So you have to keep a simple idea based on that. Okay. So it is also over. Now we can move to the next topic. The topic is types of redox reaction. Types of redox reaction. Let's check it. And the section is listen. It is types of redox reaction. Different types of redox reaction. Listen. Types of redox reaction. Okay. And the first one, that is intermolecular redox reaction. Intermolecular redox reaction. Let your redox reaction be RR. Redox reaction be RR. So we have intermolecular redox reaction. Intermolecular redox reaction means, what do you mean by the term intermolecular? Intermolecular means between two molecules or between two species. So redox reaction between two species, or redox reaction which taking place between two molecules, okay, or two species. So redox reaction, let me define the category. Redox reaction taking place between redox reaction taking place between two species. or between two molecules. Molecules may be atoms or elements. Okay. Listen, let I have a simple example. C plus O2 gives CO2. Fine. And this is a redox reaction, right? There is no doubt because carbon is in 0 and oxygen is in 0. Now the carbon is in +4, so carbon undergoes oxidation. Now the oxygen which is in -2, oxygen undergoes reduction. So this is a redox reaction, and the redox reaction which is taking place between two oxidation and reduction is between two molecules. Let's have another example. Any type of combination reaction you can add. Okay. 4Al plus 3O2 gives 2Al2O3. Ready? Yeah. So aluminum is in 0 and oxygen is in 0. Now the aluminum is in +3, oxygen is in -2. What happens? Aluminum have 0 to +3 oxidation and oxygen 0 to -2 reduction. And the oxidation and reduction is between two elements or between two species. And that is said to be intermolecular redox reaction. Between. Then there will be a corresponding intra term, right? You know, intermolecular hydrogen bonding and intramolecular hydrogen bonding, like that. Okay. So, like intermolecular hydrogen bonding, if intermolecular redox reaction is there, then there will be a chance for intramolecular redox reaction also. Intramolecular redox reaction. Then what about the category intramolecular redox reaction? If the redox reaction is within a species, if the redox reaction which is taking place within a species, that is said to be intramolecular redox reaction. So redox reaction taking place within a species, and it is taking place within a species. Okay, and you can consider any kind of decomposition reaction as 2HGO gives 2Hg plus O2. So decomposition of mercuric oxide to form mercury. Fine. So here the mercury +2, oxygen -2. Ready. And here the mercury 0, oxygen 0. So there is a oxidation reduction, right? So mercury from +2 to 0, what happens? Electron gained, reduction. Okay. And oxygen from -2 to 0. -2 to 0, electron is lost. Fine. So oxygen undergoes oxidation and mercury undergoes reduction. Agreed? Yeah. But that reduction and oxidation taking place within a single species. That species, mercuric oxide. And the reduction, the exchange of electron, that means oxidation and reduction, losing and gaining of electron, which taking place within a species. And it is within mercuric oxide. And it is not between like carbon and oxygen. It is not between two different species. Ready? Yeah. Another example, let's have the most familiar decomposition of PCl5. PCl5 decomposed to form PCl3 plus Cl2. Ready? Oh, the phosphorus is in +5 and chlorine is in -5. And here phosphorus is in +3 and here the chlorine is in 0. So phosphorus from +5 to 3, reduction, chlorine from -1 to 0, oxidation, and the exchange of electron, which means losing and gaining, is between this, within that species, within that PCl5. So that oxidation reduction which is taking place within that species or within PCl5. That's why it is said to be intramolecular redox reaction. Okay. Moving to the next two very similar type of category. Okay, which is given in your textbook as combination redox reaction. What it is? Combination redox reaction. So the next category, combination redox reaction. Combination redox reaction means, you know the term combination. It is combining. Okay. So combination redox reaction is a redox reaction in which two or more species. The species may be elements or molecules. Minimum requirement is two species. and they combined. It may be 2 or it may be 3, and they together combine to form a single species, a single compound. Ready? So this is a type of redox reaction where 2 or more species, and the species may be elements or compound, which combined to form a single entity. Which combine to form a single entity. Ready? Yeah. Listen here. Let we have 2 KCl. This is a molecule plus 3 O2. This is another element. And they together combine to form 2 KClO3. Okay. This is a type of combination reaction. Where chlorine is in -1, oxygen is in 0. Now the chlorine which is in +5, oxygen is in -2. What happens? Chlorine oxidized, oxygen reduced. So this is a redox reaction where a molecule and an element which combine to form a single compound. Like that. Okay. Another example is 2 Mg plus O2 gives 2 MgO. It's a simple one. 2 Mg plus O2 gives 2 MgO. Like that. So here 0, 0. And here +2, here -2. So this is an element, this is also an element. They together combine to form a single compound. So this is an example for your combination redox reaction. Combination redox reaction. Okay. That is an example for combination redox reaction. Fine. Let's check the next category. Is it okay? Yeah. The next category, that is decomposition redox reaction. Decomposition redox reaction. The next category is decomposition redox reaction. What it is? Decomposition redox reaction. What do you mean by decomposition redox reaction? And this is something which is opposed to combination. It is decomposed. So a single compound, a single entity, a single one which splitted to form more than one species. And this formed species may be molecular elements like that. Okay. So a single species splitted up to form more than one species. Splitted up to form more than one species. Ready? Yeah. We have the well familiar decomposition of, or the chemical volcano reaction, the decomposition of ammonium dichromate. So your ammonium dichromate on heating, what happens? It is splitted to form N2 plus the green colored Cr2O3 plus 2H2. So a single compound which splitted to form more than one species. So there is 3 species, right? Yeah. And the nitrogen is in -3, hydrogen is in +1 here, chromium is in +6 here, oxygen is in -3 here. You know how to calculate it, okay? And now the nitrogen which is turns to 0, and the chromium which turns to +3, oxygen which turns to -2, hydrogen which turns to +1, oxygen to -2. So it is clear that there is no change for your hydrogen and oxygen. It is before and after, it is in +1 and -2 respectively. Hydrogen +1 and oxygen -2. And the change that is for your nitrogen and chromium, the nitrogen from -3 to 0, that means nitrogen undergoes what? Nitrogen undergoes oxidation, and chromium which undergoes reduction. So this is a redox reaction. Moreover, it is a splitting one. A single compound will split it up. And this will be an example for your intramolecular redox reaction. And the above mentioned category is an example for intermolecular redox reaction. Fine. So moving to the next example. Example will be ammonium nitrate. The decomposition of ammonium nitrate, NH4NO3, which decomposed. Listen here. Here, one of the nitrogen is in plus 3. Sorry. This is in minus 3 and this is in plus 3. Which on thermal decomposition, it become N2O and 2H2O. N2O and 2H2O. Ready? So minus 3 to plus 1. Minus 3 to plus 1. What it is? Oxidation. And plus 3 to plus 1. That is reduction. Okay. And very same in the case of ammonium nitrite also. You know, NH4NO2 nitrite, NH4NO3 nitrate, which on heating will liberates nitrogen, pure nitrogen, plus 2H2O. Ready? For the nitrogen, I'm sorry. Here the nitrogen is in plus 5. Here the nitrogen plus 3 and minus 3. Okay? And it becomes 0. So both oxidation and reduction are all decomposition. So a single entity is split into different. So decomposition redox reaction. Wait, I'll give you one note point. The thermal decomposition on heating. Thermal decomposition of metal carbonates. Thermal decomposition of metal carbonates. Not an example for. It is not an example for redox reaction. Okay. Listen. We have one kind of thermal decomposition, that is the thermal decomposition of calcium carbonate, which decompose to form calcium oxide and CO2. From considering the oxidation state, your calcium is in plus 2, carbon is in plus 4, oxygen is in minus 2, calcium plus 2, oxygen minus 2, carbon plus 2, plus 4, oxygen minus 2, like. So there is no change in oxidation state, but this is only an example for decomposition reaction and not an example for decomposition redox reaction. Okay.